Hello, it's Stat 135, Lecture 29. Last time we finished Chapter 11. We did non-parametric tests for comparing the distribution of two continuous populations. Today we're going to go back to parametric tests, and this is in Chapter 12, normal theory, the F-test, and we're comparing the means of two or more continuous populations. So this is a generalization of the parametric tests in Chapter 11, namely the t-test. So Section 12.2 is on analysis of variance, or ANOVA. We're going to concentrate on a one-way layout, which is an experimental design in which independent measurements are made under each of several treatments. A two-way layout would add, for example, a gender to each treatment group. So it's just more complicated, perhaps more realistic in what you might actually want to do, but the ideas of the one-way layout is sufficient to give you an idea about what ANOVA is all about. So in the picture below, we have 10 independent observations for each of 7 groups. So here is a chemical concentration for each of 7 groups. And in the figure below, I make a box plot for each of those labs. And I indicate in red the group mean, and the middle line in the box, of course, is the median, but let's pretend that it's the group mean. Then alpha I would be the differential effect of the treatment mean for group I. So the null hypothesis is going to be that all of these differential effects, alpha I, is 0. In other words, that all of the group means are the same and equal to mu. And the alternative is that at least one of these alpha i's is not 0. So the question here is, are the means of each treatment group the same, or at least one of the means different? If we have 2 groups, then we could answer this question with a t-test. So this is a normal theory. We're going to be using the F statistic, and because I can't stand having J be rows and I be columns, I'm just going to transpose this picture here so that my labs are the rows and the observations are the columns. So like this. So Yij is the jth observation of the ith treatment group, and for each row I have a group mean. So for the first row, y bar 1 dot is the first row mean, and the average of the row means is y bar dot dot. That's the group average. So we have a model here, namely that Yij is mu, which is the overall mean, plus alpha I, which is the differential effect of the ith treatment, plus some noise, which is distributed normal 0 sigma squared. So if you didn't have this noise term, then for the ith row, all of the values would be the same. It would be mu plus alpha I. But we have some variation in the values of the ith treatment group, and that variation is normally distributed, centered at mu plus alpha I, and with variance sigma squared. We normalize the alpha I so that their sum is 0. The null hypothesis is that all the alpha i's are 0, and the alternative is that not all the alpha i's are 0. So now ANOVA is based on the decomposition of the total variance of your data into the intragroup variance, or SSW, and the intergroup variance, SSB. So in this picture here, okay, now the concentration values for all the 7 labs, there is variance in those values. So that variance, I would call the sum of squares total. That can be decomposed in terms of the variance within each lab and the variance of the means between the labs. So look at the bar, the middle bar for each box in the box plot. There's variance in those values. So the variance of those mean values is called the sum of squares between, and the variance within each box, the variance of values within each lab, that's called the sum of squares within. So the interplay between those two is very important for what we're about to do. To understand why, we look at the F distribution. This is going to be our test statistic. The F distribution is a ratio of 2 chi-squares, each divided by its degrees of freedom. For us, the chi-squares that we're going to look at is SSB over sigma squared. That's going to be a chi-squared with I minus 1 degrees of freedom, so I divide it by I minus 1. And SSW over sigma squared, that's going to be a chi-squared with I times j minus 1 degrees of freedom. So this is how we're going to use SSB and SSW here. Now, the way to interpret this is coming from the following theorem in your book. Essentially, on average, the SSW is I times j minus 1 sigma squared. And on average, SSB is j times the sum of these differential treatment effects plus I minus 1 sigma squared. Now, if the null is true, that means that all the alpha i's are 0. So in that case, the average SSB over I minus 1 is sigma squared, and the average SSW over I j minus 1 is sigma squared. So F will be approximately 1. If the null is not true, then at least one of the alpha i's is positive, is not 0. And so so what that tells us is that the expectation for SSB over I minus 1 will be greater than expectation of SSW over I j minus 1, so F will be greater than 1. So this gives us our strategy. So let's say that we had a distribution, an F distribution 2, 6, that would have the picture shown here. And let's say that we get a test statistic of 12. That would be in the tails. That's quite a bit different than 1. So we could compute the p-value using R, and we would see that it's less than alpha, and we would reject the null. So that's how we're going to fit these things together, and what we need to talk about now is what exactly is SSB and SSW. So let's understand in particular why SSB over sigma squared is chi-squared with I minus 1 degrees of freedom, and SSW over sigma squared is chi-squared with I times j minus 1 degrees of freedom. So in fact, we have a decomposition. So SST is SSW plus SSB. I've written down the definitions for these sum of squares, and it should make sense to you. And so this is a decomposition of the total spread of your data into the spread within and the spread between. Now, there's an algebraic proof of this decomposition on page 408. I'll skip it because it doesn't give you a lot of insight. Rather, we'll work it out for an example. Some facts from chapter 6 that you need to know is that if x1 to xn are IID normal mu sigma squared, then x bar and xj minus x bar are independent random variables. And furthermore, n minus 1 times the sample variance over sigma squared is a chi-squared with n minus 1 degrees of freedom. So now I claim that SSW and SSB are independent random variables. You can see that SSB is a function of the row means, because even the total mean is a function of the row means. So SSB is certainly then a function of the row means, and SSW is a function of Yij minus the row means. So now Y, the row means, is x bar in fact 1, and SSW and Yij minus Y, the row mean, is xj minus x bar in fact 1 above. So that shows then that SSW and SSB are independent since it's a function of, since they're functions of things that are independent of one another. So here's an example. I is 3, j is 3, so I have 3 boxes. I draw j from each box. Let's say that I get this 3 by 3 with these values. So I've written out the row means and the total mean. I can calculate the SST. It's 30. And under the null, we would have I times j draws from a single box. So SST over ij minus 1 is the sample variance, and hence SST over sigma squared is a chi-squared with ij minus 1 degrees of freedom. And so we'll say that SST has ij minus 1 degrees of freedom. Next time we're going to do the same thing for SSW and SSB. Can't wait to see you next time.